So, I will just revisit the conclusion of Toda's theorem. So, in last class we kind of quickly looked over why Bp dot parity dot p is in p to the sharp p, but let us just go over that argument once again. Okay. So, what we had were these two functions. Okay. So, we defined the function g of x as cardinality of the set of all certificates y such that y had length p of x and x comma y belong to the language L1, right? Yeah. Okay. So, L1 was that parity p language. Okay. And we also had this function h of x, which was the sum over all y's, okay, such that y has length p of x of the values chi m x comma y. Okay. So, where this m was this parity p machine with its modulus boosted up to some 2 to the power q n. Okay. And because of the way we define these two functions, what we had was that h of x is equal to 2 to the power q n minus g of x, where this q basically comes from the polynomial p. So, I think we defined it as 3 p n. So, q of n is okay. So, we had this. So, now the thing is how do we get our p to the sharp p machine? So, let L be a language in Bp dot parity dot p. Okay. So, we want to show that this is in p to the sharp p. So, given x, what do we do? So, we have this L, but I will not give the p to the sharp p machine right now. So, let us so what was the notation? N, right. So, we construct a non-deterministic machine n such that for all x chi n of x would be equal to our h of x. Okay. So, this is what we want. So, how do we construct this machine? So, given x, so h of x is just sum of all these terms. So, we guess a y, and then simulate the machine M on x comma y, right. So, now by definition this machine n will have h of x many accepting paths. Okay. And since we have a non-deterministic machine n which has h of x accepting paths, so this implies that h of x is in sharp p. Okay. So, now this is basically the oracle that we will use to get our p to the sharp p upper bound on L. Yes. No, that is what we set it to be. So, so to boost the modulus, so if you look at that lemma, so last time when we gave that lemma, so that was for all polynomials q. Okay. So, for any polynomial q given any parity p language, we can boost the modulus of that parity p language to 2 to the power q. Okay. So, we start with basically a BP machine. Okay. So, the BP machine uses some number of random string which is some polynomial. So, let us say that polynomial is p. So, given such a p, we choose our q of n to be 3 times p of n. So, yeah, so that is what we discussed last time while giving the proof of this equality. So, why 3 to the power p n will 3 times p n will suffice. Yeah, so what do we do now? Okay. So, let us say we will construct a machine n tilde which is a p to the power sharp p machine for L. So, given x, okay, compute h of x by making a query to the oracle, and from h of x compute g of x, which is just a subtraction. And now, if once you know g of x, so g of x is the number of certificates of for a string x to belong to L1, okay. And since L1 is a BP language, the number of certificates is either greater than 2/3 the number of total possible certificates or less than 1/3 the number of total possible certificates. So, if g of x is greater than, let us say, half times 2 to the power p x, then accept, else reject, because we have the promise. So, that is all. Okay. So, any questions? Yeah. So, capital M was that machine, so the parity P machine with this boosted modulus. Okay. So, we saw that given any language in parity P, we can, and any for any polynomial q, we can construct a machine M, okay, which will have this property that if x belongs to L, then the number of accepting paths is -1 congruent to -1 mod 2 to the power q, and if x does not belong to L, then the number of paths is congruent to 0 mod 2 to the power q. So, M is basically that machine. Yeah. Okay. So, yeah. So, I will yeah, so this completes our discussion on Toda's theorem. So, what we will do next is that is next week so I already mentioned that the language SharpSat is complete for Sharp P, right, and that basically follows from the observation that Cook's reduction is parsimonious. So, whenever given any input, the Boolean formula that is constructed has the same number of satisfying assignments as the number of accepting paths of that input on the given non-deterministic machine. So, we will also look at another very important Sharp P problem, which is known as the permanent problem. Okay. So, I will just briefly define what that problem is. So, let M be a n cross n matrix. Okay. So, the permanent of M is defined as the product over all permutations of n. Okay. So, sigma belonging to this set S of n. So, this set is set of all permutations of okay of summation over right. So, summation over all permutations of product. Yeah. A I sigma of I, and this I runs from 1 to n. Okay. So, sigma I is basically the element where I is getting sent to. So, this is what the function permanent is, and this is very similar to another function which all of you are more familiar with, which is the determinant function, and that has a similar definition except for one small change. There is a sign factor. So, when you consider these products, sorry, so I am using M here. So, there is a sign of the permutation that is considered as well. Okay. And the surprising thing is, although this is just a small mathematical change between the two definition, but the complexity theoretic change that happens as a result of this is quite vast. Okay. So, permanent is actually hard for Sharp P, whereas determinant can be shown to be contained in P. In fact, it is in NC 2. Okay, and the P algorithm is again quite simple. It is basically the Gaussian elimination. Okay. So, if you apply Gaussian elimination on a matrix, you only need to apply this polynomially many times to get a diagonal matrix, and then once you have that, it is just a product of the diagonals times whatever Gaussian elimination steps that you applied. So, that will give a polynomial time algorithm. and but this is a much harder problem. So, we will look at why this is sharply hard next class. Okay.